model. Yeah, just one word about the new setup. So we arrived today at the seminar room in Tromsø, and we discovered that apparently the projector has been disconnected, and that we are now supposed to use a big LCD screen instead, which is good because it's providing much better colors. The downside is it is not yet connected to the video system apparently. So what we're trying to do now is we can try two things. One thing we're trying right now is we're focusing the camera on the screen and Roberto at the same time, so that you can possibly see this well. Otherwise, you have another option still. Roberto sent the slides to you by email, so you can also, if you want, show the slides with your projector on your screen. So that's up to you. But we can, if does it look okay? Can you see the screen properly? Yeah. Good enough. Yeah. Okay, then we can try it like this.
So good afternoon. So Magnus will introduce the title. Questions already?
Now, Oslo, can you please switch off your microphone?
No. You mean Oslo?
Okay.
That's us.
Simon, the remote, just the remote, you can mute it there. Just point it up.
Okay, great. So good afternoon again. Magnus already introduced the title of my presentation. I'm going to show the work we've been doing in the past 3-4 years on PCMSolver, which is, as the title says, an application programming interface for the Polarizable Continuum model. So I will try to outline what is the problem we're trying to solve, the problem domain, what's our model, the PCM, and the programming strategies we've tried to adhere to, modular code development, and I will describe the library and present some applications that we've done with it. Okay, so what's the problem domain? So we are interested in treating systems that are in solution, so molecules or molecules in complex environments. So it is clear that these types of systems have great relevance for chemistry, of course, because chemistry almost always happens in solution, and there's a number of effects that we have to be able to describe in a balanced way if we want to be able to reproduce or predict experiment. And of course, whenever we want to treat these type of systems in a quantum mechanical model, we're faced with two main problems. The first one is that the size prohibits the use of high accuracy models, because of course we cannot run really accurate QM methods on systems of really large sizes. And the other problem is that these systems might have a huge number of conformations, and it is not possible to reproduce experiment or try to predict the results of experiments just basing ourselves on a QM run on just one snapshot of a possibly really large conformational space. So this introduces the need of conformational sampling, which is an additional problem if we want to treat solvation or structured environment like proteins. So what is the idea here? To simplify this the ab initio treatment of these systems is to use multiscale models. Basically, we try to get the best of both worlds, meaning that we describe the chemically relevant part of the system with a QM method, high-level method, can be DFT, coupled cluster, or whatever. And the part of the system that influences the chemically relevant part, but is not responsible, for example, for the reactivity or the spectroscopic response, like the barrier structure around the GFP or the solvent molecules in a solution, we describe with a classical model. So this classical model can either be focused, or in our case, the model that we choose, a continuum. So in this case, the quantum part will be the molecule of interest, while the solvent will be replaced by a continuum dielectric. So we remove all chemical detail from the picture and just use classical electrostatics in continuous media as represented by a dielectric. So what do we get from this model? Of course, the representation is really simplified, so we have no chemical detail. We've removed that. Of course, this has an advantage. The advantage is that since we will use macroscopic dielectric constant, macroscopic properties of the solvent, statistical averaging is in the model by construction. We do not have a model for dispersion and repulsion unless we add it approximately on top. But we get exact electrostatics because the description is exact and recovers the Coulomb interaction between the solid charge density and the continuum. And of course, we get self-consistent polarization as described by the Poisson equation. So mathematically, how do we deal with this? So we imagine that we have a molecule inside the cavity in the continuum, and this molecule is a source of classical Coulomb interaction. So it's just modeled as a charge density, and it can either be a QM charge density or a classical charge density. Inside the cavity, we have this charge density in vacuum, while outside we have our dielectric continuum characterized by a given permittivity, epsilon. And this is a problem that is well known in classical electrostatics. It's called the transmission problem. So basically we have a differential operator inside, which should be an Abla square. So we have the Poisson equation inside where the charge density resides, and given differential operator outside that depends on what type of environment we have. And of course, we have jump conditions for the solution to the differential equation for its normal derivative and decay conditions. So what is important to note is that both these operators, Li and Le, are elliptical. This means that we can define the solution to this problem in terms of potentials. Instead of trying to find the potential in space, or trying to then find at each point in space what's the potential, we want to find what is the representation of this potential inside the cavity, because that's the place where the chemically important part of the system is. So we split this U, the solution, into the electrostatic potential generated by the charge density rho inside the cavity in vacuum, plus what is called the reaction potential that we will represent as the charge density that is spread over the cavity. So this object is something that lives only on the cavity and can be found as the unique solution to an integral equation reported here, where the R and S operators are now integral operators. And this equation features on the right-hand side the electrostatic potential generated in vacuum by the charge density, and on the left-hand side as unknown the apparent surface charge sigma. And this equation is completely independent of the way we define the environment, since it depends solely on the form of the Green's function associated with the differential operators L that I have presented before. So this same equation can be used whenever you have a homogeneous and isotropic environment, which is most of the cases of application of the PCM, or if you have a tensorial permittivity, or a spatially dependent permittivity, or damped Coulomb, so ionic liquid represented via the linearized Poisson-Boltzmann equation, or the conductor-like screening model, Cosmo, when you apply conductor-like boundary conditions. Okay, so how do we solve this problem? So now we went from a set of differential equations defined in all space to an integral equation defined on a surface. So at this point, we have to find some way to solve this equation, and what we use is the same as a finite element method, but applied on the boundary of the cavity. So we first create the cavity, and this is made up of interlocking atom center spheres. As you can see, this is the case of benzene. We subdivide this surface into MTS small finite elements. We can either use spherical polygons or patches with other topologies. That doesn't really matter. What's important is that once we have defined discretized representation of the surface, we then attach a basis of functions that are piecewise regular on these finite elements, and we can proceed to form the boundary integral representation of the operators in the equation. So these are basically matrices of dimension NTS times NTS. And now Q and V are the correspond to the sigma and phi in the infinite basis integral equation. So basically the upper surface charges at each point on this finite element and the corresponding molecular electrostatic potential. Of course, once we have this linear system of equation, we have to find a way to solve it. In principle, this system of equation can be dense, so appropriate strategies should be devised if the system becomes really large and it's not possible to do a direct inversion. Again, what's important to note is that this is the same equation in case you have isotropic environment or conductor-like boundary conditions or anisotropic environment. And most of all, this is independent of the QM method, because the only mention that we have to the QM method here, it's in the way we calculate the electrostatic potential. But once we have the electrostatic potential, then this equation can be is well defined and can be solved for any type of environment. So, and this is what basically the idea behind trying to write standalone module for the PCM, and can be exemplified with this small diagram. So if we look at how one would couple self-consistent field description of a solute, so basically R3-FOC and DFT, with PCM for taking into account solvation effects, one would of course need to build the cavity, but that is known once one has the geometry. And then once one has the cavity, one can build the integral operators. And in the SCF cycle, what one would need is to calculate the molecular electrostatic potential at each iteration, this phi of sigma on the cavity. And that is known once one, of course, has the density matrix. Given the molecular electrostatic potential, we can solve the PCM equation to find the sigma. This can be used to form the energy correction for solvation effects to be added on top of the energy of the molecule. The FOC matrix that now features an additional term due to the solvent. Of course, one would iterate this until convergence, but there's only basically one step that is needed more on the QM host, that is basically calculating these integrals and contracting either with the density matrix or with the charge density on the surface of the cavity. Okay, so this is basically what pushed us to try and develop a code that could be interfaced with many QM codes to provide this functionality. Of course, that was one of the reasons. That's the science reason, and of course, there's also a computer science reason, if you wish, is that we want to adopt a modular style of development. That means that we want to build parts of a larger systems that can do one thing and do it well. And basically, the guiding principle behind this idea is that in computer science, you can define these concepts of coupling and cohesion that describe how programming system, or in general, a piece of software is structured. So if you have something that is really strongly coupled, you have something that is more or less like this. So basically, a component is strongly coupled to many other components, so it's not easy to remove that and switch for something else. So basically, the situation that we want to end up is something that is loosely coupled, so that if a component is removed from the system, it's rather easy to replace it with something else. The question one could ask to see if the system is highly coupled or not is, can I deassemble the system and reassemble it easily? And of course, the other guiding principle is that of high cohesion. So basically, we want to do just one thing and be able to do that really well. We don't want to have a Swiss Army knife module or a Swiss Army knife subroutine that can do everything, but it's really hard to reason about and it's really hard to debug. So guiding principles, again, loose coupling and high cohesion. And how do we do that? We go towards what's called application programming interfaces in computer science. So basically a set of subroutine protocols, tools, whatever, for building software for smaller components. So we want to have these small building blocks that can be fit together, disassembled, reassembled in other orders, or substituted for something else. And how do we do that? Of course, we have to make clear to whatever wants to use our code how our code works. And how is that done? Okay, so we first of all have to encapsulate our capabilities, meaning that we want to expose to the world only what we want other people to use. So the internals of the code have to be hidden, not because we don't want other people to see those, but because it's not interesting and it's not important to use our functionality. Then, of course, a really handy thing is to have own development history. So for your own API or your own module, you would like to be able to track what happened in the past and possibly switch back to past versions. You have to document your code, because otherwise reading code is not a fun experience. It's really not fun. So you have to explain in plain words what you can do and what each function can do, or each component of the API. It can be other stuff than just functions. You have to provide a version so that people that want to use the functionality you provide can choose in between different versions and decide which version is the best for their applications. Of course, you need testing, because you need to be able to find out if you messed up at some point and how to recover from this. And most importantly, I think something that probably is overlooked is that the thing is to be able to be, you have to be able to build this piece of code on its own, so that it can be tested independently and from any other host code. So if you have a plugin, you have to be able to test the plugin independent of the other stuff where you might plug this thing in. And of course, deploying, you have to find a way to make this thing available to the public. So how would you release it? Is it tarball, or you have precompiled binaries, or whatever? But of course, you have to think about this stuff. So, and this is what we came up with for the PCM. The name is PCMSolver. So it is open source licensed, LGPL version 3, and it's mainly developed on GitLab, but there's a front end on GitHub so that people can get the code directly from there. And it's synced with our publicly released version. It's, I would say, rather compact piece of code, because it's 5,000 lines of C++ and circa 3,000 lines of Fortran. And again, the main idea is to try to implement what I showed in the previous diagram. If we have a QM host program, represented here by this box, once there's a program-side interface where our plugin can come in, the only exchange of information in between the two that is necessary, it's really each iteration, either couple cluster or SCF, it doesn't really matter, or what QM level of theory, is communicating the electrostatic potential back to the module, and the module has to be able to communicate the surface charge back to the QM program. So this is the only communication essential in between the two. That's what we try to implement. So what can our module do at the moment? So we have the traditional collocation solvers that are also available in Gaussian. We have isotropic and anisotropic Green's functions, and we have work in progress on wavelet solvers, and I will show you an example of that later, and on real-time solver. So to be able to follow the time evolution of the surface charge following, for example, an excitation process in the solvent module. As build system, we use CMake with the AutoCMake plugin manager that Radovan created, and we can build static and shared libraries. So it depends on your taste, which one you prefer. The API is written in pure C to guarantee interoperability, but of course we have Fortran bindings that can be built on demand. Testing, I was mentioning, we use this C++ framework for testing. It's called Catch. At the moment, we have 51 tests on the master branch, and we also test independently the whole interfacing procedure. So we have small programs that test actually the API and not only the internals. And we have continuous integration on the master and the release branches and some of the hidden branches, both on Travis CI and Magnum CI, that are two online services. So the release process, as I said, mentioned already, we have a public repo on GitHub, so all the tagged versions are available there. We have a private repo on GitLab, where some of the private development goes on. And there's a Break-on-Byte library that is served on the Anaconda cloud service, thanks to Laurie Burns at Georgia Tech. Documentation, we use Doxygen for in-code documentation, but we extract that using Sphinx, so that everything, both the documentation for the users that doesn't fit in the code and the in-code documentation, are served online on Read the Docs, and you can read the documentation at this website. Okay, so which programs are we currently interfaced with? It's 6, so I would say a good number. Dalton, LS Dalton, Cypher, Dirac, Respect, and Koala. And what's the advantage for us, apart from having these nice slides? It's that, of course, we have separation of concerns, so we don't need to be concerned on, for example, how the implementation of the electrostatic potential integrals is done, or how the SCF process is managed, or the linear response solver. So separation of concerns, and of course we can leverage the functionality of each of the other codes. So we can basically put our plugin in and get the PCM working, and then leverage whatever a specific program is strong at. So for example, with Dalton and OpenRSP, in collaboration with Magnus and Arvin here in Tromsø, we have open-ended response theory. We got that working. In Cypher, it's mainly to play around with the coupled cluster code. In Dirac and Respect for relativistic effects. And in Koala, which is Sebastian Oefener's program in Karlsruhe, for frozen density embedding. Now come 3 small examples. I'm not going into much detail for this. So I was mentioning Dirac and Respect for relativistic effects. So basically the idea is that we can explore the method axis or the basis set axis. Oh, that's not really interesting. But we also want to be able to explore the Hamiltonian axis. Sorry, here it's capped. It's supposed to show non-relativistic 2-component, 4-component. Sorry. We want to be able to explore these axes too, and see what's the combined effect of relativity and solvation on spectroscopic properties, for example. And basically we showed in this first paper with Trond and Radovan that the Fock matrix is only modified on the diagonal blocks, the large, and small. So basically formulation is rather transparent with respect to addition using of a more advanced Hamiltonian. And the workflow that I showed in the flowchart before is exactly the same as for one component. All the details of calculating the integrals that are now slightly more complicated because we have more basis functions, kinetic balance, and so on, are hidden in the QM program, so we don't need to care about that. So this thing was first presented, as said, with Trond and Radovan for electric properties, static electric properties, and we've recently extended it to EPR and PNMR parameters, and this was shown by Kenneth in 4 weeks ago. Then I mentioned the wavelet solvers. So why are we interested in using wavelets to solve a boundary integral equation? Because whenever you do a naive boundary element method implementation, you might end up with a problem that is not sparse. It's a dense linear problem, which of course one can solve with iterative methods, but it's really hard to get that to work in a really efficient manner for really large systems. While when using wavelets, you get automatically a sparse representation. So basically you get a system matrix that has the structure where there's lots of zeros and really few entries that are non-zero. And you can prove that this type of representation for the operators needed for the PCM as a linear memory code. So this thing can be stored in memory and is linearly proportional to the number of finite elements you put on the cavity. And of course, then you can use all sparse matrix technology to solve the system equations in linear time. The problem, although, is that when you use this type of parameterization, you get a huge number of points on the surface, and on these points you then need to calculate electrostatic potential integrals. So let's see here, for example, if we have a piecewise linear wavelet basis, already at the coarses level, we have 23,000 odd number of points where to evaluate the integrals. Of course, you get basically a converged result already at this level, but that becomes really costly. So there's more work to be done on this. And finally, as a last example, I was mentioning non-homogeneous environments. And by non-homogeneous environments, we mean, for example, a blob, a droplet with a certain permittivity that is embedded in a larger medium with another permittivity. And in between the two, we put a sigmoidal profile to switch in between the two permittivities. And we can use this to model, of course, droplets or membranes and see how the phase transfer of molecules in between these two different permittivity is affected. Okay, so come to the acknowledgements. Of course, my supervisor, Luca, Radovan, for lots of discussions on implementation and modular program design. And Dr. Laurie Burns at Georgia Tech for showing me how to work with Anaconda, and also for lots of discussion on CMake and modularity. Of course, you for your attention. And again, the slides are there if you want to refer to them. Thanks.
All right, thank you, Roberto, for the talk. We'll open for questions. Are there any questions here from Tromsø? Go ahead, please, Bingo.
Yeah, I have a few questions first. No. Oh, okay. One question is, I understand that PCMSolver also needs some results from the host program, like OpenSP, right? And how do you get this? Like, does PCMSolver calculate the integral by itself, or
no.
use callback?
So what I removed those slides because otherwise it would be talk would have been too long. But so technically, what we need is a potential at the points on the cavity. So it's a vector, and we pass back a vector with those potential transformed to the charge representation. So that's the only communication mainly. How do we do that? We internally have a map. So basically an associative array with a label for the potential and a pointer to the data. Okay, so each vector is labeled with a certain label, the molecular electrostatic potential from the nuclei. And whenever we need to communicate this thing, the host program refers to it by label. And internally we use this associative array between labels and data.
Okay, the
host so it's everything on the host side. We don't manage integrals or integral matrices, because at this level of formulation it is not needed. Okay, here. So the electrostatic potential is the integrals contracted with the density. So it is, in principle, you would need 3 index quantity, because you have 2 indices for the AO basis plus 1 for the finite element on the cavity. But at this point, you contract 2 of the 3 with the density matrix. Okay, so here you pass a 1 index object. Again, the sigma is a 1 index object, and you pass it here. Again, this phi kappa lambda s is a 3 index object, but then you contract 1 of the 3 to get a 2 index object. And this contraction is done inside the host program. We don't do that, so we don't need to deal with higher than 1 index quantities.
Which, in other words, host program sends this as an argument to a code, but not to callback during running.
Yeah.
So another question is, PSolver is part of PCMSolver or not?
Yes, by B I mean because it can either be the boundary element solver. So it can either be by collocation or by a Galerkin method. So either with the wavelets or the not wavelet method. So the equation is generic, and the way we communicate with the host program is independent of which type of solver we use.
And Also, I noticed here in this flow chart, your final result is as a kind of fork matrix added by PCM contribution.
Yeah.
So the different histogram has different type of matrix. How do you solve this now?
No, again, we only communicate vectors. So,
arrays.
Yeah, arrays.
Oh.
So we are not tied to a particular representation for that.
Yeah.
But yeah, I mean, it's not general by any means, because this is the particular problem that lends itself to.
No.
I mean, this is easier than what you try to do with OpenRSP, because then you need to know multi-index things. And yeah.
My last question is, how about PCMSolver in MRCAM, right? Because you in 6 programs, there's no MRCAM.
Yeah, we haven't
What's the
thought about we haven't thought about that actually. Luca? PCMSolver in MRCAM? Why haven't we tried? I don't know.
We are thinking of a different way of doing it, like having something without a cavity, but not directly with PCM, not directly at the surface. We're thinking to solve the strength of the MRCAM program is that you can solve the 3D problem. So then you don't have to map it to a 2D on the surface, but you solve it in 3D directly. That's what we would like.
So that's differently from PCMSolver. Oh. Thank you.
Thanks.
More questions for Tromsø? No? How about Oslo? There's one question.
Yeah, Simon?
Is the microphone on? Can you hear me? Or?
Yeah.
Yes.
Yeah. Okay. Good. I'm wondering if it's always kind of like a hard boundary between the cavity and the continuum, or could there be some kind of damping function, some soft function in between?
Yeah, that has been done, or at least has been proposed by somebody. We don't have it implemented, and I think there is some technicality involved in formulating at least the conditions on the boundary, because then if you have a floating boundary, I'm not exactly sure if it can be exactly mapped to one integral equation, or rather you would need a finite element method for that. Luca has a comment.
But do you think more in terms of a cavity that can be moved, or more like a permittivity that doesn't change sharply from one value to the other?
Yeah,
you don't have a boundary. You don't have a boundary in a sense. You just have a permittivity that is position dependent. That would be the way to do it in MRCAM, because then you just solve the problem in 3D. You don't really have a boundary anymore. You just have a permittivity that is changing in value.
I see. Okay.
Yeah. It would be a more complicated Poisson problem, but it's just a Poisson problem in 3D then.
Okay, thank you.
Yeah, thanks.
All right, so there were no more questions from Tromsø, and were there any more from Oslo? That does not seem to be the case, so we will thank the speaker again.
Thanks.
Everyone, a nice weekend, and see you next week, I guess.
And we will try to fix this screen problem till next week.
Everybody sign this.